All right, so.
I remember the first time. That was a bad day for us.
All right, so astronomical seeing. This talk was born out of my realization that most of the talking I do to new astronomers is about why the image in their telescope looks like crap. You know, they go out, spend a lot of money on a telescope, and then they're disappointed. And I understand that. I did the same thing. And it took years of looking through my telescope and working on telescopes to start to understand why they can look bad, when they will look bad, and honestly, when they do great. I have a 13-inch Coulter. They were not expensive telescopes when they were new. The quality was hit and miss. I got one of the hits. And honestly, when it's right, it's one of the finest looking telescopes I've ever looked through. And when it's wrong, it's pretty nasty. But the first challenge for us around here, of course, is to get past this. This is the first stumbling block to astronomical seeing. And what I want to talk about, actually I'm going to do in the opposite order. Atmospheric conditions is what most people think about when you say something about seeing. And but a lot of times it's not that. The local conditions we'll talk about, and then telescope conditions. And these two are what people blame it on most of the time. The first thing they do is they think their telescope's out of collimation, because that's the first strange word they learned in astronomy anyway. And honestly, today's telescopes typically aren't out of collimation much, if at all, and that's typically not the worst thing wrong with the telescope. This is not what we're shooting for. Although it's a pretty picture, we want our stars a little cleaner than that. So I'm going to start with atmospheric turbulences. This is what a high magnification image of the moon looks like when the atmosphere is turbulent. Now, this atmosphere can be in several places, and we'll talk more about that. But what's happening is that, in theory, a point light source will radiate light in all directions equally. It'll be a plane wave front. It'll go out as a straight. By the time it gets to Earth, it would appear as a flat, straight wave front. If you're going to, when you start talking about light and light analysis, there's two models. You either talk about it as waves or rays. And in a ray tracing model, what happens, in a wave, that wave gets bent up. In ray tracing, these arrows get pointed in different directions, a bunch of different directions. Either way, it all amounts the same. And the larger the aperture of your telescope, the larger the effect that you'll see. So, and you know, all of that makes for pretty sunsets, but not good for astronomy. So, this picture, now one of my problems with this presentation was finding graphics that work. And you cannot, and I've been playing with cameras to try to capture this through the telescope, but trying to find cameras that are sensitive enough to record video at such low light levels, at such high magnifications, I haven't come across a combination that works yet. The best I've seen image-wise are produced out of computer models and not actual live images. But this was supposed to be an image of a building off in the horizon over a desert. And of course you had all the waviness. You've all seen it, the highway, looking down the highway or whatever, all the wavy stuff that goes on. That one didn't turn out so good. But this has to do with where you set up your telescope. And we'll talk more about that in a few minutes. Then the mid-altitude effects of the atmosphere are probably more prevalent than even the upper ones. And that is looking, and this is a great image, shows you on the windward side of the mountains, you get a nice steady image of Jupiter, not because the air is not moving, but because the air is moving in what's referred to as laminar flow. It's not turbulent, it's not boiling up and down, which is what happens behind the mountain. You get all this turbulence, and that's what it does to your image. Then the high altitude effects are the effects of the jet stream and cold fronts and other things that turn out aren't intuitive. You know, that day when a cold front moves through and all of a sudden it snaps clear and the sky is that deep dark blue, those are typically bad nights for observing, because you've got cold air that's moved in over a hot ground, and now all of a sudden you've got convective radiation going on and the air's churning this way. You try the best, I'll talk about it some more. Experience local conditions. All right, so I haven't done this in years. I used to make notes about where we got good observing. We actually do pretty good most of the time at Village Creek, and I think it's because they're on top of that hill over there. Some of the best viewing I've seen has been over there, even though we wind up sitting on top of that gravel pit of thermal radiator that we wind up sitting on, which I wish didn't happen. So most of the time, a good steady imaging is when a high pressure system has been in place for days. The ground temperature is stabilized, the air is calm, and things aren't boiling. They're not churning. And typically you'll wind up trading transparency for steadiness, especially in this part of the country. Those hot, muggy summer nights in Memphis are probably some of your steadiest imaging. Like I said, you'll trade a little transparency for that water vapor that's in the air. And there's an image that shows what happens with the cold front. In front of the cold front, you've got warm air that's not doing much. Behind it, suddenly you've got warm ground, and all this air is trying to churn, and that causes the poor imaging. There are a couple of websites. There's only one that I know of that actually tries to predict scintillation, and that's what it's called. The effect you see through the eyepiece of turbulent air is called scintillation. It's churning air isn't called scintillation. That's just turbulence. Let me see. We keep this on our website. You can get to it quickly. And it shows you three things about current and predicted conditions. Cloud cover, which, you know, white means cloud cover, dark blue means none. Transparency, the whiter it is, the worse it is, the darker blue it is, the better it is. Seeing, same kind of thing, the lighter the color, the worse it is, the darker the color, the better. And darkness, the same thing, you know, the darker it is, the better. And see, it's not going to be that. See, it's dark right now. You know why? It's clear outside. But it's going to cloud up after a while, and it's going to be not as dark. So that's showing up. Seeing is the map you want to look at. And these are all computer models. There's a guy in Canada that does this and got the Canadian government's permission to share this information, and does so free of charge. This shows a map, and you can actually get it to play. I forgot how, but you can get it to show you how these dark regions are moving around and what it might look like throughout the night. So this is one place to look. This is not the Holy Grail, okay? These are computer models. What Einstein was credited with having said, you know, all models are wrong, some are useful. This one's useful if you pay attention to what you're looking at and realize where it can be wrong. Let's see. Go back to my presentation. And then clear outside. This is a site designed specifically for astronomy. I haven't used it enough to know how accurate it is or isn't. It has a lot more variables to consider than I normally bother with. But this is today, and these are the coming hours. You've got cloud cover, all kinds of things about visibility is more like transparency, and they really don't cover scintillation, so they don't have anything about real seeing here. Okay. So, local setup conditions. Now we're starting to talk about the stuff that really impacts what you're doing. You set up out in your front yard and look over the house at something, and you've got all that hot air radiating up off the roof of the house. Same way with that asphalt and concrete road that you're setting up across the street. You know, I love observing from the house. I love when I can just roll the telescope out in the driveway, set up, and look at Jupiter, look at the bright planets. I don't do much else because too much light pollution. But, you know, the planets are great, and they're fun to look at from home. And you can spend plenty of time doing it because you don't have to drive anywhere or anything. But, you know, if you can get out in the middle of the grass, that's better than the driveway, you know. And these things do impact the view and the steadiness of the image. We've talked about it before. Anytime we talked about building an observatory or something, we talked about sitting in concrete pads so people could set up their telescopes and stuff like that. And the more I've learned, the more I think that's a bad idea. The best thing is just set up in the grass, you know. Asphalt is black, you know, it's even worse. Parking lots are bad. Again, all of it is a trade-off. If you're trying to show the public stuff, you're going to wind up on asphalt, in parking lots, under lights. And we do a lot of that, trying to get kids and people interested in astronomy and share some of the wonders of the universe. But those aren't the best views. Set up on gravel, I'm sorry, that was just me being, I'm on a tirade about that. I got another thing about Village Creek, and that is, and where's your car? You know, set it. I'm the world's worst about this. My telescope's big and heavy. I pull up my truck, I open the back end of it, I pull the telescope out and set it down. Now, more often than not, I don't bother moving my truck. But you know, if I typically park with the truck facing north, so the south is that way, which is where I do most of my observing. But if I want to look north, I will pull my truck up another 20, 30 feet. So I'm not looking back over the hot engine compartment or anything else off my truck. Telescope conditions. Collimation, of course, is what everybody blames everything on. And all that is the geometric alignment of the optical elements in the system. everything from the focuser, the eyepiece, the mirrors, the lenses. Basically, everything needs to be on a center line axis and perpendicular to that axis, unless it's a diagonal, and of course there's that. But that's collimation. That's getting everything lined up. And for the biggest part, most telescopes these days keep their optics pretty well aligned. Newtonians are the easiest thing to knock out of alignment just because of the way most of them are made. Schmidt-Casagrins, if you knock that out of alignment, shame on you. Just be careful. You can do it, but be careful. Once they're aligned, you really don't have to fool with them much, especially the secondary. And that's the one that's got screws on it, which everybody will start tweaking, and then you've got to clean it off. Then you've got to call me, and we'll fix it and get it right, and then leave it alone. But most of the time, they're fine. Refractor telescopes, if that's out of collimation, you got a serious problem. And depending on how much money it costs new, which a good APO can be many thousands of dollars, that is, send it back to the manufacturer, because I'm not going to touch it. So, geometric alignment. This is more of an issue than most people realize, and there are two reasons why your optics deform. One of them is differential cooling. You got a telescope with a mirror in it, you take it out of the hot car, set it up in the cool night, and it's going to take a few minutes for that mirror to cool down. As it does, different thicknesses in glass, different other conditions cause that glass to cool differentially, and that causes the shape of the mirror to be off. Now, what you got to realize about mirror shapes is that when I say off, I'm talking about changing the surface of the mirror. So if the mirror were, say, 4 or 5 times the diameter of this room, changing that by the width of a human hair is the kind of dimensions that we're talking about, okay? It don't have to be off much. A tenth of a wavelength will start to show up. And wavelengths are very, very short. So temperature stabilization of the glass. All right, temperature of the air. All right, so the other place where these turbulent currents occur is not just in the atmosphere, but also in the telescope. For a long time, it was believed that this was happening here in the tube. And there are conditions where that can happen. If you've got a white tube, that's probably not the case. If you've got a dark colored tube and it's been set out in the sun, you probably got issues to deal with. But most of that actually turns out to be, let me go back to this. So as this mirror cools, it's this boundary layer between the glass and the air that's constantly changing temperature. And what they found out in recent studies is this is where most of the turbulence is occurring in most telescopes. There are several ways to deal with this if your telescope's prone to it, and it includes installing fans. You basically want to get that air moving. First off, the quicker it moves, the faster it cools down, and the less of this becomes a problem. But also, if it never cooled down, if that air moving across there is laminar, then it's not a problem. So keeping the air flowing across it is the best solution. Let me go back. Transportation. So this is a place where you've got control over what's going on. I drive a truck and I carry a big telescope in it, and I've got a camper shell on the back, and it's all navy blue, if not even darker than that. So it gets warm back there in the sun. And typically what I will do, I have windows on that camper shell, one in the front of it, thank goodness, that I can drop, and then 2 vent windows in the back. And that keeps airflow going through that camper as I'm driving down the road to whatever our observing site is. And for us, that's at least 30 minutes away. If we're going to Village Creek, it's an hour, you know, whatever. So things in the truck are starting to come to temperature to begin with. If you store your telescope in the house in air conditioning and you take it outside where it's hot, you've got the same problem. It's just reversed. But then you've also got condensation to deal with too, if it's cold and you take it out where it's warm and humid. So how you transport your telescope can impact what your viewing is going to be like. The sooner you can get the telescope set up, and this is my tirade about Village Creek. We do something, and I understand why we do it, but we introduce everybody that's going to be setting up telescopes to the people that we're going to do an indoor program for. Then we all run up the hill and set up our telescopes. Well, by the time we get them out of our trucks and barely set up, the people are coming up to look out of them already. And honestly, I need another hour for my telescope to cool down, settle down, and provide a good view. I may start doing that anyway. Just get up there, get it set up anyway, and y'all come on up when you get there.
That wasn't a problem when I was doing the indoor program.
Well, and of course, the indoor program is used to take a little longer, but we can work on that too. So, transportation and setup time. Don't expect your telescope to look great in the first 15 minutes after you set it up. You go to all that trouble to get it set up, and it's going to take an hour or two to settle down. I discovered that by accident. You know, I had a 300-pound, 10-inch Parkes Cassegrain telescope, and you know, I'd break that thing down, load it up in my truck, drive out to the Wilsons, spend an hour setting it up. You know, and it's a beautiful telescope. I mean, the primary mirror in that thing was that thick. For a 10-inch mirror, that's thick. I mean, a big, beautiful mirror. Perfect optics in this thing, but it looked like hell, you know. And then I don't remember what happened, but we wound up out there for 2 or 3 hours, and I think I was looking through other people's telescopes, and I went back to mine, and suddenly the view was just incredible, you know. And that was when I started to understand what was going on. Plus, I'd been fighting with collimation on that telescope. That's another story. But and that's what you'll see, you know. Get them set up, let them stabilize. Look through them again, look through them again. We did a telescope tips video, and my point in that was we've gotten so used to our multimedia world and rapid entertainment that the idea of sitting at a telescope eyepiece and just staring at something has gotten past most of us, and turns out that those have been my first time I spent hours looking at Mars. You know, was really pretty fascinating. You can sit there and look at the eye, and suddenly it'll just snap clear, and then it's gone. You know, and you're looking at it, and it's nice and fuzzy, and it's the kind of incident where you realize after the fact that it just happened. You know, it's one of those things, it comes and goes so fast that you go, ah! And by the time you do that, it's gone again, you know. But if you sit there long enough, you get enough of those to really start to understand why Lovell saw canals, you know, why people have been able to do this for so long and see the stuff they've seen. You wait for the atmosphere to come to you, and then all of a sudden the view's there. Sometimes it's steadier than others, but spend some time at the eyepiece. If you've ever gone to a star party where you've set a telescope up and left it all day, you know, you're going to need to pay attention to thermal gain during the day. If it's set up and you've protected your telescope with, I use those lightweight Mylar reflective thermal blankets. Actually, is what they are. They're for survival things, and I cover my telescope with them. It looks like it's covered in aluminum foil, reflects all that radiation away. But at the end of the day, you take that off, and if you pay attention, the ground is radiating. And if you've got a dark tube scope like I do, that's kind of low to the ground, it's picking up that radiation in the bottom of the tube. And then you've got to deal with that differential warming again. So pay attention. You can use fans. You can do a lot of things to start dealing with local conditions and telescope conditions for studying your vision. This is stuff you can do something about. But more than anything, learn what it is you're looking at. And star testing is the best approach. You need to use basically a high magnification eyepiece, and by that I mean 1 millimeter for every F number. So if you've got an F4 telescope, a 4 or 5 millimeter eyepiece is where you should be magnification wise. If you've got an F10 Schmidt Cassegrain, a 10 millimeter would be fine. A perfect, let's see, don't I have a, yeah, all right, so perfect optics. Here is what you're looking at here is, this is what it looks like in focus. A perfectly focused star at high enough magnification will not yield a pinpoint. Okay, it just won't. There's lots of reasons for it. Most of them are diffraction within the lenses and everything else. But this is, you'll wind up with a dot with several concentric rings, and they should be even and not very bright. The inside and outside of focus should look identical, and that's just racked in and out of focus a little bit. Now, that's almost never the case. They almost never look identical inside and outside of focus, and there are lots of reasons for that, and it takes, I can't show you this or spend 5 minutes talking to you about this for you to be able to go home and star test your telescope, but I'm telling you to start learning about it. Ask at observing sessions. I've got a great book on the subject. It's up here. You can stop and take a look at it if you want to. But it will show you all the different things you can check for, including collimation, what out of collimation looks like. You can also see, I tell you the one that got me, I didn't realize it, but I've got an eyepiece that's got horrible stigmatism. And that one's where you get this egg-shaped view out when you go out of focus, and it goes 90 degrees to that when you go out of focus the other way. And that tells you you've got astigmatism. And that can be in the primary, it can be in a secondary. It's typically because of pinched optics. A piece of glass that's in a mount where it's got pressure on it where it shouldn't have pressure. Pinched primaries and big daubs are a big cause of that. All right, we need to talk about that. That's that sling I've been trying to get you to let me build. All right. And Coma is not something you probably can't do much about. Spherical aberration, it tells you what it looks like. Turned down edge. These are all mirror conditions that you're not going to be able to do much about besides resurface your mirror or trade it or something. This is what turbulence looks like. Now, this is overcorrection in a presence of turbulence. But what you get with turbulence is all these splotchy images, and the rings are uneven, they're messed up at focus. This is as good as it gets. This is the double stars, Zeta Aquarii, and these pictures were taken, I think, within 2 minutes, in a period of 2 minutes. And it shows you how the seeing can go from good to mush in just no time flat. So learning what you're looking at will help you diagnose what's going on and do something about it. Whether you can figure out whether it's something you can do something about or not. So, in the end, patience and practice are your telescope's friend. Thank you. Any questions? Yes, sir.
Are there qualitative things you do when you step outside and you try to assess whether it's going to be a good night or a bad night, other than that it's cloudy or rainy, that are helpful for you before you drag your stuff out?
No. No. It's mostly I don't trust just going outside and looking. I will get online. If it's, honestly though, here's what the truth is. The truth is around here, we get so few opportunities to go observing that if it's clear, we're going. Well, so we don't make it, I don't wait to see if it's going to be steady air. So.
Often as the evening goes on, things get better.
It does.
It can.
It can. It doesn't always. And oftentimes it's better right after dark, right after it turns dark. And then it can go bad again. I've seen that happen plenty around here. So, anything else? Bill?
When I was with the observing with the Australian groups, their philosophy was if it was scheduled, we're going. And we went out a couple of times when it was actually raining, but then some spaces opened up and we saw had some really good observing in between the rain. We just pulled back under the shed when it started raining again.
Yeah. We ought to do it anyway. If it's raining, let's stop someplace for dinner. Yes, sir.
Condensation, what's the best? Just leave it alone until it dries out, or? I know my glasses. I walk outside.
Well, yeah, you absolutely don't want to start wiping the lenses down, and if it's in if it's in a reflector telescope, just say no, don't touch it. But otherwise, I actually have a 12-volt hair dryer. Then the other thing is to keep that from happening to begin with. And to do that, you don't leave your telescope pointed at the sky. You point it at what you want to look at, then you turn it sideways or whatever, and then go look at your charts and figure out what you're going to do next. Then go point it back up. Don't leave it unattended, pointed at the sky. Yeah.
If you don't have giant eyepieces, what I usually do is keep one in my pocket and then one in the telescope.
Absolutely.
It gets it a little warmer so when you take it out, it's not going to condense
Right.
for a while.
Yeah, that's how I deal with eyepieces too. I always keep them in my pockets. I keep 2 or 3 because that way they're warm.
If you set it one of those little racks between the tripod,
The next thing you know, they're all dude up. John?
Well, one thing I was going to say is that, clouds, they're up there a lot of times and everything like that, but just because the clouds are out doesn't mean you can't take your telescope out. If you can look through the little places in the clouds and you can actually see stars, then you can take your telescope out and you can get good, good images even with a lot of clouds out.
That's
you
true.
Have to pick your holes in the clouds to see through. As long as it's not, hazy or overcast, you're fine.
The way I look at it is if the water droplets are collected in a number of places rather than spread out all over the whole sky, you've got a pretty good chance in between them.
Right. Anything else? Yes, sir.
Rick, I'm just curious, with the upcoming opposition of Mars at the end of July, what are some of the things that you would recommend for really taking advantage of this opportunity, whether it's the type of scope, whether it's binoculars, getting to a site where maybe we have the better chance of better sky conditions, other than maybe around here, where it could be hot and humid that time of year? What can we do to best take advantage of the upcoming opposition of Mars on July 27th?
Just be willing to take a telescope out anytime that the sky is clear. You can run around in the country trying to find a place where you're going to have good seeing. Guarantees are the west side of the Rocky Mountains. All right, that's the windward side. Wind's coming across those California deserts, starts to hit the mountains, go over it. There's a lot of good places in Arizona and New Mexico. It's just dry and not many clouds. Texas is not bad, but you know, being willing to get out anytime it's clear and set up and look at Mars, you'll find yourself out there that one night when everything is just right, and you'll catch images that you won't get to see again, maybe the rest of your life. I've seen some that, and for planets, long focal length. I mean, that's the deal, long focal length. Rich field telescopes are not that great for planets. You want something with a f10 or more. If you don't have that, you know, high magnification eyepieces and stop the aperture down. You don't need 24 inches of aperture to look at Mars. And you'll get less of the effect of turbulent atmosphere in a stop down aperture. In fact, the thing to do with that, with something like that, is cut 2 equal sized holes on either side of your secondary in a mask, and that way you've got the resolution power of a 24-inch mirror, but the aperture of, say, maybe a couple of 8-inch holes, and you've got the light of an 8-inch with the resolution of a 24. So there are ways to address those kind of issues, especially for something like Mars. And I do like planets. We'll take a 10 or 15 minute break and come back to hear about the end of the universe. So it won't matter about all this telescope stuff anyway.